All right, this audience looks like they are ready to start. My name is April Younglove, and I am an adult services librarian here at the library, and I help schedule programs like this one. I asked Ian Madin to come speak to us today for a couple reasons. First, I schedule the artwork in the galleries, and I saw his work through Lake Oswego Open Studios, and I thought that was very cool, and I thought that Rocks might coincide with our L.O. Reads programming this month. This month, we're reading the book Tilt by Emma Patty, and that book's theme is heavily about what it's like to be in an earthquake in the Northwest. So imagine how excited I was to learn that this artist also is a retired geologist specializing in that exact thing. So, and a citizen of Lake Oswego. So I hit the jackpot with this speaker. And also, if you are interested in earthquakes and you haven't read our L.O. Reads book yet, please do feel free to check out the book Tilt by Emma Patty, which we are all reading this week. There's more information about that over on the back table. And on the table near the door on your way out, there's a couple other things. There is a survey where you can tell us what you thought about the program, give us ideas for improvement, or tell us how great it was, etc. We love to get those surveys. That helps us. And I wanted to give a big thank you to Ian himself, who is generously offered to do this program gratis, so that is fantastic.
I could have gotten paid.
And I also wanted to mention a couple other things about Ian. Ian was featured on Oregon Field Guide, and his official title, since I wasn't saying his official title, it's Senior Scientist and Earthquake Hazard Geologist, retired. All right, Ian, you ready to take it away from there?
I am.
Okay.
All right, well, thank you all for coming out this afternoon, and thanks to the library for giving me this opportunity to both show my sculptures and also to talk to you. I'm not going to really talk specifically about the earthquake that's featured in the book Tilt, but subduction zone earthquakes are part of Oregon's long history, and so they'll be showing up from time to time. And if we have time at the end for questions, I'd be happy to take questions on just about any subject. So with that, I'm going to dive into this and give you a little background first. This series of stories, geologic stories, and the sculptures that accompany them were conceived by a colleague of mine named Matthew Packwood, who's a composer and who runs the Oregon Origin Project, which puts on annual programs that are based on either rooted in Oregon indigenous culture or Oregon's physical past. And we conceived this idea that was going to be a new symphony music piece that he was going to compose to tell Oregon's geologic history. And so we sat down and I tried to break that hundreds of millions of years worth of history into a finite number of events that I thought were significant and particularly that I thought had an impact on the landscape. So you could actually go out and see these in the modern world. And so those 10 stories became 10 movements in the symphony, which was premiered last June at the Reeser Theater. And I'll have a QR code at the end of this if you want to see a video of that performance. I created a series of sculptures that also went along with each of those 10 stories. And so let me see what the next one is, because go back here. So the idea, no, that's right. That's okay. I haven't given a presentation in a while, and I just want you to know, I've given hundreds of geology presentations. This is my first art presentation, so really exciting. Okay, so to start off, we need to understand a little bit about how the world works. So I'm going to give you a really quick primer on plate tectonics. Okay, most people probably know that the surface of the Earth is very dynamic, and big chunks of the Earth's surface move around with respect to each other. That's called plate tectonics. They bang into each other. They produce earthquakes and volcanoes. What drives this planetary machine is one very simple physical fact, and that is hot stuff rises. Now, why does that apply to the Earth? Well, oh, okay, there we go. Sorry, I'll try to stay in a little closer here. The Earth consists of a relatively thin, rigid shell of rock that we call the crust, that's perhaps 5 to 25 miles thick. That's familiar rocks like the ones that we see here on the surface. And it is thin, cold, and rigid. At the very center of the Earth is a huge ball of solid and molten iron, and it is extremely hot. And in between are a couple thousand miles of rock called the mantle. And so what happens is that the rock in the mantle gets heated by the core. And when it gets hot enough, it rises through thousands of miles of solid rock, very slowly, obviously, but it rises, and the entire mantle is in constant motion, circulating as the heat causes parts to rise. They rise to the surface and they cool against the bottom of the crust, and then they sink back down in an endless 100 million year long cycle. And so that produces several manifestations at the surface when the crust interacts with these places where the mantle is going up and going down. And so the most important of these is, or the fundamental one is what's called a spreading center. So this is, here it's called a divergent plate boundary. And so what happens is that hot rising material comes up and it sort of spreads as it gets to the base of the crust, and it actually pulls the crust apart. And a crack opens up in the crust, and molten rock that we call magma wells up into that crack and freezes to produce new crust made out of basalt, which is a basic type of volcanic rock. And then that process continues, it repeats, it cracks again, more material comes up. And so running down the middle of every ocean on Earth is a mountain range, tens of thousands of kilometers, not tens of thousands, thousands of kilometers long, completely hidden beneath the waves, at which new crust is being manufactured continually and then splitting apart. One part goes this way and one part goes that way. So out in the middle of these oceans, we're actually making new skin for the Earth, and then it's moving away at a fairly, well, at rates like a couple of inches a year over long periods of time. So that means that over a very long period of time, you've created a whole bunch more crust. But there's only so much room on the surface of the Earth, and it's a sphere, so if you spread things apart on this side, on the other side, they're going to come together. And when that happens, you get what's called a subduction zone. And that basically means a place where the crust, which is now older, because it's further spread away from that spreading center, it's colder, it starts to sink back down into the mantle. And typically those occur at a boundary between an ocean plate and a continental plate, so like between the Pacific Ocean and North America. And so that subduction zone, the crust sinks down beneath and then eventually gets down to where it's deep enough in the mantle that it starts to reheat and goes back into that cycle again. And we live adjacent to a subduction zone just off of our coast, and that's what produces the earthquake that features in the book Tilt. Because this subduction does not happen smoothly, it goes in fits and starts. So the two plates lock up for hundreds of years, and then boom, they move 50 feet in a few minutes. The other important feature that figures into Oregon's geologic history is what's called a hotspot. And so this is a fairly narrow plume of very hot rock that's risen up through the mantle, and again, impinging on the bottom of the crust. But instead of being a great big long stretched out thing that produces an ocean filling band of a spreading center to produce new crust, it's very, very focused. And so geologists, being so creative in the way we name things, call this a hotspot. And so a hotspot also figures very prominently in Oregon's geologic history. So we'll get to that sooner or later. Okay. Everybody kind of got the basics of plate tectonics? Wonderful. Let's proceed. So there are 10 of these stories, as I said, and the names for each of the stories came from a group of artists that we engaged for the Oregon Origins project, each of whom made a painting to go along with their particular story. So the names are not particularly geologic, so I just want to let you know in advance. That's why they're a little bit odd. So first one's actually fairly straightforward, exotic terrains. So let's think about that subduction process. If you go back 300 million years, the coast of North America was about at Idaho, and Oregon didn't exist. It was ocean. And it wasn't even a place on the ocean because that ocean floor underneath the water was continually moving to the west, pardon me, to the east, and being subducted underneath Idaho. So for a long period of time, this conveyor belt of ocean crust is just sliding beneath where Oregon's going to be at some point in the future, and then disappearing down the trench when it gets to Idaho. But that crust oftentimes had on top of it large volcanic island complexes. And like imagine Hawaii or even Japan. And that these had been built up onto that moving ocean crust. And so they're sort of big lumps that are going along on top. Imagine, you're walking on the conveyor belt at the airport trying to get to your gate. And you spill your sandwich onto the moving walkway. Well, most of that moving walkway, when it gets to the end, just happily goes around the edge. But your sandwich is going to get stuck there. And so this is what happens with these big ocean islands, is that when they get to the subduction zone, they jam into the subduction zone, they break off, the subduction zone moves out a little bit, and that chunk of rock gets plastered onto the edge of the continent. And so over the period of about 150 million years, Oregon was steadily built out from that original subduction zone in where Idaho currently sits, out to its current level by adding every 10 or 20 million years, adding another chunk of exotic rock. And so we call these exotic terrains because they came from someplace far away. One of the very first ones that showed up, we call the Wallowa terrain because it shows up in the Wallowa Mountains, has limestone deposits that were formed in coral reefs in the tropics. So in order to have gotten to our latitude, they have to have moved 1,000 miles. And it's hard to imagine big pieces of rock like that moving that far, but remember, we have millions and millions of years to do it. And it's amazing what you can do if you take 5 inches a year and run it for a couple of million years. So that is what has built out the deep bedrock that underlies much of Oregon. And we don't see it exposed in many places. You can see on this figure here, the places that are dark green are where it's actually exposed at the surface. Everything else is covered with younger rock. And then this boundary is about the edge of where we assume those rocks are no longer present. And we'll see what fills in that corner shortly. And so the stone that I chose to illustrate this is something called blue schist. And just a quick note about these time stones. The idea was each sculpture was made from a rock that represented the particular event that it was associated with. And because geologists are very focused on time and order and succession, each sculpture has to be sitting on top of a rock that's older than it or from the previous event, because that's what we call stratigraphic position, that the younger rock is always over the older rock. And so this is, maybe just a not terribly significant thing, but it was part of my vision for this series of sculptures, that each piece would be sitting on a base that was derived from the older or previous section. And so here's the problem, because this is our oldest rock, the blue schist. This piece on top is our oldest rock in unit. It's the exotic terrain. So what's older than that? What do you represent what happened before as to provide as a base? And so the answer here is that this is a piece of peridotite. Peridotite is the rock that makes up the mantle of the Earth. And so the mantle was always there and therefore kind of predates the blue schist. Blue schist is a very interesting rock. It forms when basalt, which is, remember, what makes up most of that ocean crust, it's produced at the spreading center. If you drag it deep into the earth very, very rapidly, if you take it down 20 miles really quickly, and then you pop it back up to the surface, it's exposed to extreme pressure, but it doesn't spend enough time in the depths to heat up. And so you get a very unusual assemblage of minerals, one of which is called glaucophane, which is bright blue. And so it's a rock that has a very unique origin, and it's fairly rare. And if you want to see a great example of that, go to the jetty at Bandon and walk out on the South Jetty, and it's made out of blue schist, and it's the most fabulous rock imaginable. Okay, we're going to move on to the next event, which is the birth of Cascadia. So starting about 50 million years ago, a hotspot reached the surface of the Earth off of what was then the coast of Oregon. And it produced an enormous volcanic eruption that produced a great big island, ocean island complex made out of basalt that was probably about 300 or 400 miles long north to south and maybe 50 miles east to west. So again, this is sort of like an island the size of Japan. And it was produced largely out of a rock that we call pillow basalt. And that forms when basalt erupts underwater. What happens is that the molten lava freezes instantly against the water. But the pressure is building up behind that frozen surface. And so a little crack will appear, and it squirts out a bit of that molten lava that it's like squirting toothpaste out of a tube, and then that freezes immediately. And so you build up this rock that's a series of these tubular-shaped blobs of basalt that are just sort of squirting out one after the other, piling up on top of each other. And so that produces a distinctive rock called pillow basalt that tells us that was erupted deep in the ocean. Eventually, that layer got so thick, it's about 20 miles thick, that it got above the surface of the water, and then we have some more normal rocks up there. But this great big island arc or island complex that we call Silesia, named after exposures on the Siletz River, then drifted to the east along with the subducting ocean floor, and it was the last piece that sort of filled out the basement rocks of Oregon. It basically choked off the subduction zone that was occurring at the time, and a new one formed to the west of it, and that's the modern configuration now. We have that subduction zone on the west side of Silesia. So this is the last piece of the puzzle that filled out the entire basement, if you will, of Oregon. And this photograph shows an example of pillows. You can kind of see that there are sort of a bunch of round features here. This is looking, it's sort of cut across the toothpaste tubes. Or hot dogs, however you want to think about it. And you can kind of see this sort of stack of round pieces. I realize it's not super obvious. There's a really great place if you go to Depot Bay on the south side of the Dee River and climb down on the rocks there. Those are all pillow basalts, and they're really quite cool. So the rock that it represents this is a piece of pillow basalt breccia. And so as those pillars are forming, little bits and pieces are breaking off them all the time, and they pile up on the ocean floor and make a big pile of broken rock. And any rock that is made of broken fragments we call a breccia. And then over time, that rock has been cemented with calcite, calcium carbonate, a common mineral that grows in ocean environments. And so the white and pink material that you see is calcite that has cemented the black basalt bits. And this is mounted on a base of serpentine. Serpentine is a rock that we commonly find in the exotic terrains because it forms down in the mantle when water reacts with the peridotite in the mantle, and the serpentine is very, very low density. And so it rises like a hot air balloon through the solid crust, and we find it sort of separating all of these exotic terrains because it comes up along the faults that bound them. The next event is called, and I'm not even going to try and pronounce this, this is the Hannes Kuz word for tides. And this is a period when all of the plate tectonic action had kind of settled out. The exotic terrains had all been accreted. Everything had stabilized. Oregon was covered with an ocean that was the location for the deposition of sedimentary rocks, mudstone, sandstone, conglomerate, limestone, on the floor of that ancient ocean. These were the first rocks that were actually deposited in Oregon, in the place that they are, as opposed to being transported from someplace else. And so a great example of that is the sandstone down at Shore Acres Park, down outside of Coos Bay, where there's these fabulous sandstone layers. People go down there when there are big waves because the waves crash against these things, and it's just fabulous. And there's great botanical garden there too. Definitely you should go visit that. And this is a rock that represents that. This is a piece of mudstone from very near that spot at Shore Acres. Mudstone, as the name sounds, is very fine clay and mud that has been cemented together. Typically, this doesn't make a very good rock for making sculpture because it tends to be very soft and crumbly, but there's a layer of it down there near Coos Bay that is incredibly hard and dense and compact and takes a really high polish and allows you to cut a really sharp edge. And so this is a piece from that location, a piece that was tumbled by the waves, and I've shaped it and polished it on one side. It is sitting on a base of porphyritic basalt. This is basalt that has, normally basalt is very fine grained, has no visible crystals in it. If it sits beneath the Earth's surface for a while before it actually erupts, oftentimes that's enough time for crystals to begin to grow. And so when the rock then comes out on the surface, it freezes very quickly, but it's preserved those larger crystals, typically of plagioclase, which is a clear or white mineral. And so this is, you can kind of see these white flecks in here. That is the plagioclase that is making this a porphyritic rock. And this is a rock that was part of that Silesia island complex. The next event is called, again, the artist came up with these. I think this one's actually pretty cool. The Seeking Fire. So we've got our basement rocks in place. Subduction is going on basically in the location that it's going on today. Miles and miles and miles of ocean floor are descending beneath the edge of North America, beneath Oregon. And when those rocks get deep enough in the earth, they begin to cause melting of the overlying material, which produces a chain of volcanoes, like the current Cascades. And this is one of the hallmarks of a subduction zone, is what we call a volcanic arc. And they are typically a fairly narrow band of volcanoes. And the great example of this, of course, is the Ring of Fire. We have volcanoes like this in Alaska, the Aleutian Islands, Kamchatka Peninsula, Japan, all down the Andes, are these narrow bands of volcanoes that are being fed by the subduction process. But you can see here, and again, the dark orange is where these rocks are visible today. The light orange is where they're buried underneath younger rocks. This is spread out over all of Oregon. It's not a nice narrow band like we would normally expect. And so the question is, why is this happening? And the answer is the hotspot, remember, that produced Silesia back here at 50 million years. It is, and so here's one of the characteristics of the hotspot that I forgot to mention. They are fixed in the mantle. So as a plate moves over them, they appear to move across the plate. And the classic example of this is Hawaii. The big island is right on top of the hotspot. Every other island is successively older and successively further from the hotspot. And once you get beyond the last of the Hawaiian Islands, there's an underwater seamount that has been basically eroded down below the waves, and another one, and that a chain of seamounts extends for 1,000 miles across the Pacific Ocean floor, just straight as an arrow, because that's the pathway that the plate has taken across the hotspot, and it's just left behind these remnant volcanoes, showing the place that it went. So we had that hotspot over here off the coast. It produced Silesia, and then the whole shebang, the North American continent and the subduction zone, drifted over the hotspot. So underneath all of Central Oregon now, that hotspot is coming up underneath the crust, and it's trying to melt its way through and find places to get through. And so we have volcanic activity that's spread out pretty much all over the state. And this produces some of our iconic landslides, landscapes like the Painted Hills, which are layers of volcanic ash produced by big eruptions, explosive eruptions during this period. And this lasted from about 40 million years ago to 16 million years ago. The rock that I chose to represent this is what's called a tuff. And so this is what happens when you have a big volcanic explosive eruption. We call that a caldera eruption. There's a great big blister of magma sitting beneath the surface. It's typically what's called rhyolite magma, which is the chemical composition. It's very sticky and pasty, and it's charged with a lot of gas. And as it gets closer and closer to the surface, eventually it cracks its way through to the surface enough that it starts to release the pressure, and that gas comes out of solution in this molten rock and turns into a foam, and we call that foam pumice. And pumice is basically a sponge made out of volcanic glass. But that expansion into pumice increases the volume of the magma by 100-fold. And so when you rapidly increase the volume of something, that's an explosion. And so that blows a huge amount of ash and pumice and bits and pieces of rock from the surrounding volcano into the sky, and it rains down around and builds up oftentimes into a thick enough layer that it can basically cement itself back together. So if you look at this piece, the pink background is ash, the white are little pieces of pumice, and the black pieces are chunks of rock that were ripped out of the throat of the volcano. And it is sitting on a base of sandstone from down on the Rogue River that was part of those early marine sedimentary rocks that were deposited after the exotic terrains and Silesia all settled down. The next event is called, by the artist, the ecstatic immemorial, which is quite a name to live up to. But this is what geologists call the Columbia River flood basalts. And this is truly a stupendous event geologically. Basically what happened is the hotspot is either the hotspot is moving to the east or the continent is moving to the west, same idea, but the position of the hotspot gets further and further east, and eventually it gets to the point where it's able to break right through to the surface as opposed to being sort of diffused under Central Oregon. And that sets off a huge outpouring of very, very fluid basalt lava. So when you see pictures of volcanic eruptions in Iceland or in Hawaii at Kilauea, that's basalt. And you can see it flows like water downhill. So that's a characteristic of basalt. It erupts very, very high temperatures, 2,000 degrees, so it can flow quite a long way. These eruptions came out of a series of giant fissures in the ground that were oriented along the Oregon, Idaho, Washington border. And you've seen recently these photos of the Iceland eruption where there's a long crack in the ground and stuff is fountaining out of that along the entire crack, and then lava is flowing away from that. Okay, imagine that, but 100 times or 1,000 times bigger. The Columbia River basalt eruptions produce so much lava at such a high rate that They flowed from Oregon, Idaho, Washington border area, Hell's Canyon, all the way across Oregon and Washington to the Pacific Ocean, into the ocean, down the submarine canyon at the mouth of the Columbia River, squeezed their way into the sediment that was making up the banks of the submarine canyon, and traveled another 40 or 50 miles underground before they finally came to rest and froze into buried bodies of basalt. 400 or 500 miles for one individual lava flow that probably happened over the course of a few weeks or a few months. When this was done, most of eastern Washington and eastern Oregon was a featureless plain of bare black rock. And then it happened again and again. 100 times it happened over a span of perhaps 1 million years. Out underneath the Tri-Cities, Kennewick, Pasco, and can't remember the third one, Richland, thank you. It's 2 miles thick. Here beneath our feet, it's 600 feet thick. See, if you've been to Yaquina Head out at Newport, that's Columbia River basalt. The basalt not only traveled underground under the sediment beneath the sea, in places it erupted back onto the sea floor because there was so much lava pushing behind it. So this was truly a spectacular and stupendous event. And associated with that, there was a bunch of giant caldera eruptions, much like the one that you saw in the previous sculpture, that produced some of the most fabulous scenery that we have out along the Owyhee River, where we have big deposits of tuff that erode into these fabulous fingers and shape, this pink and gold rock. If you've ever been to Leslie Gulch, there's a great place to go visit and see these incredible spires and castles that are made out of this tuff that was part of the Columbia River basalt eruption. And the piece that I chose for this is a piece of, this is classic Columbia River basalt. It's dense, black rock with no features. This is from a quarry out near Biggs Junction. And this particular lava flow was 300 feet thick. And this is from the bottom 5 or 10 feet of that lava flow. So it cooled under a tremendous amount of pressure and became very, very hard and dense. And so when they got in there and started doing the quarrying, this rock breaks with what we call a conchoidal fracture. That means that it makes sort of curved shapes that are the same idea that when you're making an obsidian arrowhead, if you apply a point of pressure to the obsidian, it will flake off a curved piece. And so you can see some of that curved nature here in this fractured surface. And it is mounted on a piece of rhyolite lava, which is from the previous event. This one was from out near Pineville. And rhyolite is the other end of the spectrum from basalt. It is, the basalt is relatively low in silica, which is the main component of volcanic rocks. Basalt is 50% silica. Rhyolite is 70% silica. And it makes that pasty lava that usually explodes and makes calderas and tuffs. But sometimes you can actually get little flows of rhyolite, and it produces a very colorful rock. The next event, upwelling. So this isn't actually a rock. This is a process and a landscape. So if you look at a map of Nevada, the thing that's most prominent about it is that there's a series of skinny, long, north-south directed mountain ranges and intervening basins that usually have dry lake beds in them. And we call this the basin and range. And what's happening in the basin and range is that a large area of the mantle underneath Nevada is hot compared to the surrounding mantle. And so hot stuff rises. So underneath Nevada, there's this big blister of mantles slowly rising. The crust sitting on top of it is rigid, so it doesn't stretch. The mantle is plastic, so it does stretch. So in order to accommodate the fact that when you bow something up like that, the top surface gets longer, you have to stretch the crust. And the way that that's accomplished is by breaking the crust up into a series of slivers and then having them spread apart. And so the way to think about this is, let's say I've got a bunch of books on a shelf, and they're all the same size, and they're all lined up next to each other. They occupy this much space on the shelf. If I flop them over on their side, sorry librarians, now they occupy a whole bunch more shelf space. And if you look at the top edge of the books, when they were all together, it was nice and flat. When you flop it over, you go up the cover of one book across the pages, down, up, down, up, down, up, down. That's what's happening in Nevada with the crust. It's broken up into a bunch of sort of book-shaped slivers that are tilting over like this so that they can stretch out. And the ranges are the places where the material is going up, and the basins are the places where it's going down. That extends into southern Oregon, into this area that is outlined in tan, and all of these black lines are some of the major basin and range faults. So Abert Rim and Abert Lake, Winter Rim and Summer Lake, Steens Mountain and the Alvord Desert are all examples of basin and range faults producing an uplifted basin and a downdropped, an uplifted range and a downdropped basin. So, and this process has been going on for about 6 million years and is going on today. When we go out and look at these faults, we can see places on the ground where the ground actually broke during the last earthquake that they had a few thousand years ago, has not been yet eroded or erased by erosion. So we know that this process is actively happening. So this is a little bit difficult because remember that it's not a rock, it's a process and a landscape. So I did find one rock, though, to represent this. This is a piece of basalt that comes from the fault zone that separates the Egley Rim from Silver Lake Basin, which is, if you've ever driven out, I'm sure everybody's done this, you drive from Silver Lake down to Summer Lake, and you go over Picture Rock Pass, and you go up that fault zone. There's a long grade there. And so the basalt came out of that fault zone, and it is coated with red iron oxide and white calcite, calcium carbonate, that were deposited by hot springs fluids that were using the fault as a pathway to get to the surface. So this piece of rock actually is very closely related to the faulting activity. And it is on a base of what we call the rattlesnake welded tuff, which is, again, one of these giant caldera eruptions that produces a huge cloud of pumice and ash and rock, falls to the ground. It, in this case, was so hot and so thick that when it came to rest, it actually fused together into a solid mass of glass. All the pieces of pumice that were around originally got flattened into thin strips. And the thing that's amazing about the rattlesnake ash flow tuff is that the eruption was so big that as this material fell back to the ground, it actually came down at such a high rate that it flowed away across the landscape, away from the caldera, as a sheet of red-hot gas and ash and pumice and rock moving 60 miles an hour. And we find it extending up to 100 miles away from the crater, so it was still a flowing mass 100 miles away. So it covered a huge area out there in eastern Oregon. So the next event, which is called Bloom, this is when the subduction volcanoes finally get their act together to produce a proper volcanic arc. So the subduction has now been going on long enough. The effects of the hotspot are long since gone because it's off on its way to Yellowstone. That's where it is right now. And so now we're producing a nice narrow chain of volcanoes sitting right on top of the subduction zone that are the kind of configuration that we see today. And the big volcanoes that we see there, Mount Hood, Mount Jefferson, Three Sisters, those are actually relatively short-lived features. They last about 500,000 years, and then the magma feeding them is depleted. They get ground down by glaciers, so you end up with things like Mount Washington or Three-Fingered Jack, and then a new volcano pops up someplace else. So there's sort of this cycle of Mount Hoods being built and then worn away, and another one coming up someplace else, producing this very narrow chain that we call the High Cascades. Crater Lake is a classic example of this. It's interesting. Crater Lake is one of the few volcanoes in the Cascade volcanic arc that actually has big explosive eruptions. Most of the time, they're much more like Mount Hood, which generally has what we call dome building eruptions, where it squeezes out a bunch of magma into a big pile that eventually collapses under its own weight and sort of builds up a layer of volcanic rubble around the mountain, and then a lava flow will come out over the top of that and cement it together, and then you'll get some more rubble, some more ash, some more lava flows, and you get a series of layers or strata, so we call that a stratovolcano. So that's what virtually all the volcanoes in the Cascades are, is stratovolcanoes except for Crater Lake. And the rock that I chose for this is a piece of pumice from Crater Lake. And the interesting thing about this piece of pumice, so again, remember, this is that magma that's sitting under the ground there. It's got a lot of silica in it. It's rhyolite magma. It's got a lot of gas in it, and it burst into foam when it was depressurized, like taking the top off a beer bottle. And that material then was ejected into the sky. This piece of rock I picked up 35 miles away from the crater. So it was thrown through the air 35 miles. This piece is about that large. I have a piece from the same size that's that big around that was thrown that far. It was either thrown 35 miles or it was blown so high in the sky that it got into the jet stream for a little bit and was carried and then fell out again. So that was a truly tremendous eruption, but really tiny compared to that rattlesnake eruption that I just talked about. This was another challenge to come up with an appropriate base to go underneath this, because remember, the previous thing was the upwelling, the basin and range faulting. Hard to find a rock for that. But this is a piece of travertine, which is calcium carbonate or limestone that's been deposited by springs that were coming up along the fault that bounds the Abert Rim and Lake Abert. And it was coming up when underneath the lake, when the lake was higher, and as that hot material came up the fault and encountered the lake water, it precipitated out this white calcium carbonate surrounding all the boulders on the beach of that particular incarnation of the lake, producing these thick layers of travertine. Lake Abert. Lake Abert is just southeast of Summer Lake and north of, oh, there we go. Thank you. Well, okay, this is Summer Lake here, and Lake Abert is, over here. And now we're just I've lost control. Okay. We're on to the next event, which is the ice ages. So starting about 2.5 million years ago, there were global changes in climate that resulted in the onset of a series of ice ages. And we've all sort of heard of the ice ages, but it's what people often don't realize is that there wasn't just one. There were lots of them, and they extended back several million years into the past. The nature of ice ages is they tend to obliterate, each new one tends to obliterate the evidence of the previous one. So it's a little bit difficult to trace back very much beyond 2 or 3 of these. But we actually have a really good record of these older ones. When we look at sediments in the ocean, we can tell when ocean level was going up and down, because during the peak of an ice age, so much water is tied up as ice on the land that the sea level drops dramatically. And so that produces a signature that we can see in sediments in the ocean so that we can determine actually how many of these events occurred well over the past. So there's several really obvious manifestations of ice ages. The most common of which is, of course, glaciers. Enough snow falls every year, or more snow falls every year than melts away. That snow compacts into ice. Eventually, when it gets thick enough, the ice flows very slowly. And as it does so, it grinds out a valley and picks up pieces of rock. And when eventually it gets to the point where more ice is melting away than is coming down the valley, all the rock that was embedded in it is exposed and left behind in a pile that we call a moraine. And so the classic example of that here is the moraines that bound Wallowa Lake. You can see these very uniform ridges. So when these moraines were formed, everything between the two moraine crests, here. So here's one crest. I need a pointer. Here's the other crest. Everything between those two, was completely filled with ice that probably extended about 100 or more feet above the level of those moraines. And the ice was continued to flow down into that space and melt away. The rock that it was carrying, that it had ripped out of the mountains up above, was left behind in these great big piles. And then eventually, when all the ice melted away, we have the lake left behind, hemmed in by those moraine deposits. But there are other really big impacts on the landscape besides moraines, and there are two of those are what we call pluvial lakes and loess. So remember, the basin and range, we pull the crust apart, we make a series of rising basins and rising ranges and falling basins, and those are oftentimes completely enclosed. There's no drainage out of them because the tectonic motion, the faulting, is faster than a stream can cut its way out and get up a pathway to the sea. So all of those closed basins in Nevada and in southeast Oregon filled up with giant lakes during the ice ages because the climate was wetter. There was more snow and ice on the local mountains. And so in places like, again, Summer Lake, I'm going to try and do this without shifting to the next thing. So here we have Summer Lake. That was part of a giant lake complex that was 250 feet deep and that is now just about 6 inches deep on a good day at the end of the snowmelt season. And another great one that people may be familiar with is the Fort Rock Basin that includes Fort Rock and Christmas Valley. Again, enormous lakes. And the thing that's really important to think about is that during that period, all of these areas that we now see as desert actually had lush vegetation surrounding the lakes, big freshwater lakes, fish in the lakes, wildlife, and quite a large native populations lived around the margins of those lakes. And then the loess, the entire northern hemisphere was covered by a single ice sheet. And it, of course, ground a whole bunch of rock up as it moved across Canada and British Columbia and the northern U.S. And then when it got to the edge where the ice was melting away, all that ground up rock or rock flour eventually got melted out of the ice, got picked up by rivers and deposited on the floodplains of those rivers. And then when those dried out, the wind picked up that fine silt material and blew it out to the south and the east, sort of away from the ice sheet. And the reason that happens is the ice sheet's very cold and it's very high because it's so thick. And so you have what's called a katabatic wind, which is the air that's chilled on top of the ice flows down and away from the ice. And so you would have this constant howling gale coming off of the ice sheet. Where it came out into eastern Oregon, it produced a thick layer of wind-blown silt that we call loess that covers much of the Columbia Basin in Oregon, and some of it even extends up into the Portland Hills, where we call it the Portland Hills silt. For the sculpture for this piece, this is a piece of basalt, actually from the exotic terrains up in the Wallowa Mountains, that was incorporated into the glacier and then ended up in one of those moraines that I just showed you for the bound Wallowa Lake. And it's sitting on top of a piece of a lava that we call dacite lava that was collected from Mount Hood. And if we have more time, I can tell you about the snowflakes, but I'm going to have time for questions. The next event, now we're getting closer and closer to the present, is the artist's name is Stasis Torrent. Geologists call this the Missoula floods or the Ice Age floods. So that ice sheet that covered the northern hemisphere, when it got as far south as Missoula, Montana, it blocked up the Clark Fork of the Columbia River at Missoula. And behind that ice dam, a lake filled up, filling the entire Bitterroot Valley, which is like 45 miles long and 20 or 30 miles wide. The lake was a half a mile deep. And so the lake got deeper and deeper and deeper. But of course, ice floats. So eventually, when the water gets deep enough, the dam that's holding it in floats. And as soon as it floats, it breaks up. And all that water goes rushing down the Clark Fork, across eastern Washington, through the Wallula Gap at Hermiston, on down the Columbia, through the Columbia River Gorge, into the Portland metropolitan area, and eventually on out to sea, producing an absolutely enormous flood. The largest floods here in the Portland area, the water level was at 400 feet above sea level. So we are at about maybe 175 here, so the water here would have been 225 feet deep. In the gorge, it was 700 or 800 feet deep, probably moving at 60 or 80 miles an hour, and of course carrying pieces of ice and rock and everything that wasn't nailed down, and a lot of stuff that had been nailed down. It was ripped out of the walls of the gorge by that flowing water. And it got into the Portland area, and a little ways downstream at Kalama, there's a sort of a narrow spot in the Columbia Valley, and that slowed the water down enough that it filled up the Portland area and backed up into the Willamette Valley all the way to Eugene and filled the entire Tualatin Valley. And that produced a thin layer of silt throughout that entire area that settled out of this slowly moving water. And then finally the flood receded and went away. But the ice didn't stop. Remember, the ice is continuing to flow. It's a continental ice sheet. Nothing stops it. So the dam formed again, and the lake built. And then it floated, and it broke, and the flood happened again. So we know of at least 40 of these floods that occurred in succession on a cycle of maybe 50 or 60 years, starting about 12,000 years ago to, between about 15 and 12,000 years ago. And there's pretty good evidence that there were people in the area at the time, and that there are native stories among the indigenous tribes in the area that record these tremendous events. The piece of rock that I chose for this is what's called a porphyry. Remember we talked about the porphyritic basalt earlier? This is the same idea. Big crystals grow in the magma while it's underground, and then they get frozen when it reaches the surface. I don't know where this came from. I know where I found it. I found it out by Arlington in the gorge. The rock could have come from Canada. It probably did come from Canada. It was carried in an iceberg, or it was carried in the ice sheet until it got to the dam. And then when the dam broke, it was carried in an iceberg that floated it all the way down to Arlington, where that iceberg came to rest, melted away, and left this rock behind. And it is actually, it's mounted on a piece of glacial, another piece of that glacial material from the moraines out at Wallowa Lake. And finally, we come to the present. And the You know the story of the present. You live in the present. The image that I provided here is just to give you a little sense for the amount of impact that we have made in an incredibly short period of time from a geologic perspective. The areas in yellow are areas that are currently being used for agriculture. All the black lines are roads. It's a little hard to see up close, but you can see in the urban areas there's huge concentrations of roads. And all the green areas are forest lands that are being managed for timber, about 90% of which have been cut at least once. So this is just to give you a sense for the amount of Oregon's land surface that we have modified in some way. Humans are an incredibly strong impact on the landscape. We rival many geologic features and processes in terms of the amount of impact that we make. And of course, global warming, climate change is another manifestation of that that's hard to put on a slide. And so the sculpture that I produced for this one, it's kind of hard to find a rock that is younger than the arrival of European settlers in North America, but we live in Lake Oswego. Does anybody know what people were doing down in Old Town in Lake Oswego in the 1800s? We were smelting iron, mined from the Columbia River basalt. Remember, that came all the way from Idaho. They got iron ore out of that. They smelted it down along the Willamette River, and so they'd melt up a whole bunch of ore, and then the molten iron was denser than the residue and the impurities, and so they would tap that off, and then they would take all that molten rock material that was the impurities in the ore, and they would dump it over the edge of the river and down into the Willamette, producing a little layer of natural glass or slag. And so there are deposits in several places along the shoreline here at Lake Oswego of this slag. So this is a piece of that slag collected from out of the river, mounted on a piece of Columbia River basalt that was deposited by the Missoula floods out near where Bridgeport Village currently is, which is on the site of what used to be a gravel pit that was mining gravel that was ripped out of Lake Oswego by the Missoula floods and dumped there. So very, very topical and close to home. Okay, so that's the end of my presentation. We've got a few minutes for questions, and I'll be happy to stand outside here if you don't get your question to answer once they throw us out. Very quickly, if you want to see the video of the Birth of Cascadia performance that includes the music, the art, and another version of this lecture, you can use this QR code. And if you want to see my website and see more of the work that I do, that's that QR code over there. This exhibit of sculpture, along with a lot of explanatory material, is going to be on display at the Rice Museum of Rocks and Minerals out in Hillsborough, starting probably within a month or two, be there for a year. So if you are interested, go out there this summer and have a look. Even if you don't want to go out there for the Oregon Timestones, the museum has incredible specimens of rocks and minerals from all over the world. It's a great place to go. So with that, thank you very much for attending, and thanks again to the library. Okay, questions until they throw us out. Yes, ma'am. Yeah, okay, so that's kind of inside ball with seismologists. It doesn't change the big picture of Cascadia Subduction Zone earthquakes. The big picture is, in the last 10,000 years, there have been 19 earthquakes that broke the subduction zone from Cape Mendocino in Northern California all the way to Vancouver Island, producing a magnitude 9 earthquake. Within the Juan de Fuca plate, there are several zones that produce much smaller earthquakes much more frequently that are places where the plate is breaking up internally. That probably does not have much impact on what the big subduction zone earthquakes look like. Oh, okay. All right.
I'm so sorry, you're gonna have to talk to him
Okay.
out there.
Like I said, I'll be happy to stand out under the cover and